If you could come in and get seated, that would be great. Is DNS privacy. And our first speaker is Laura Roberts from Princeton University. So welcome.
All right, thank you. So good afternoon. I'm Laura Roberts, and I'm excited to talk to you about our paper entitled The Effect of DNS on Tor's Anonymity. This was joint work with Benjamin Greshbach, Tobias Puls, Philip Winter, and Nick Feimster. So let me begin by telling you why we started working on this topic in the first place. So Tor is an anonymity network that allows people to browse the web anonymously. It's also known as a system that can circumvent government censorship. However, some Tor users end up with pages like this when they browse websites that are blocked in some places. For example, this happened when a user tried to access adult content with an exit relay located in Indonesia. And then the situation looks similar with exit relays located in India. So here, the so-called competent authority didn't like the adult content domain name that the user was trying to access, so the authority blocked the site. So this demonstrates that Tor isn't magically transporting users' traffic into uncensored territory. Instead, users are still subject to interference at exit relays, and in this case, DNS is being used to conduct this interference. So let me give you a quick overview of how DNS works in Tor. So here we have a Tor client on the left, the Tor network in the middle, a DNS resolver on top, and the example.com web server on the right. The client is going to attempt to resolve the example.com domain name. Recall that DNS traffic is unencrypted, so we can't have the Tor client ask its DNS resolver about websites it wants to visit over Tor, because this would allow the client's ISP, the resolver itself, and other adversaries to learn what website the client wants to connect to, which defeats the whole purpose of Tor. Instead, DNS queries are sent through Tor, just like web traffic, and exit relays are the ones who are responsible for performing DNS resolution for Tor clients. Before our work, we knew very little about what happens once a DNS query is sent through Tor, and what we knew was based on anecdotal evidence. For example, we didn't know what DNS resolvers exit relays were set up to use. We suspected that some performed their own DNS resolution and that some used third-party resolvers such as Google's public DNS resolver, but we didn't know what else was being done. We also didn't know what autonomous systems the DNS queries were traversing. And we didn't know how these resolvers worked. And as my example at the beginning of the talk showed, the resolved domains weren't always what we expected. So in our work, we wanted to shed light on this resolution process, and in particular, we wanted to learn how DNS could be used to compromise Tor users' anonymity. The first question we wanted to answer is, how exposed are DNS queries? Normally, in past traffic correlation studies, researchers have only worried about the TCP traffic coming out of Tor and not the DNS traffic coming out of Tor. And this is because past work has shown that an attacker who can see traffic going into Tor and coming out of Tor can potentially link the two and figure out what website a Tor user is visiting. So then we wondered if there are parts of the internet that get to observe DNS traffic coming out of Tor and not the TCP traffic coming out, and what the possibilities are for leveraging that DNS traffic. So here's a visualization of what I mean, and we'll go through this together. So we had a computer in AS88, which is Princeton University, and from that computer, we fetched the website Baidu.com. Before fetching that website, we needed to resolve the domain name. Our computer ran its own DNS resolver, which means that it did iterative domain name resolution, starting from the DNS root server, and then making its way down the DNS delegation path. Here we show all the ASs that were traversed as part of this process. Notice that we traversed 4 ASs for the web traffic, but 13 for the DNS traffic, and 11 of those ASs were traversed only by DNS traffic. To get a better idea of the situation, we repeated the same experiment for the Alexa Top 1000 sites. And as a result of our experiment, we found that for half of all of the Alexa Top 1000 sites, DNS-only ASs accounted for 57% or more of all traversed ASs. So getting back to Tor, this means that an exit relay that's set up to do its own resolution exposes revealing DNS traffic to ASs that don't have the opportunity to observe the corresponding TCP traffic. We concluded from this experiment that DNS traffic is exposed to parts of the internet that subsequent web traffic is not, and this means that there's a class of adversary that we had been ignoring thus far. So now that we know that we should probably pay more attention to DNS resolution in Tor, the next question for us was to understand how exit relays are set up to perform DNS resolution. That is, we were wondering how many of them are set up to use Google's public resolver versus how many are set up to do their own resolution, etc., because this has quite some impact on anonymity. We designed an experiment to answer this question, and we took the following steps. So step 1, we set up our own DNS server for a website domain that we own. Step 2, using our exit map tool, which is a tool that we maintain and can run a networking task over all exit relays, we made each Tor exit relay resolve a subdomain name that was under our control. We gave each exit relay its own unique subdomain name to resolve so that we could tell them apart and so we wouldn't hit a cache. For step 3, we inspected our DNS server logs, and if an exit relay does its own resolution, then we expect to see its IP address in our log. If it uses a third-party resolver, then we expect to see an unrelated IP address in our log. We ran this experiment from September of 2015 to May 2016, at least once a day. Here are the results of our experiment. In this table, we're showing you the minimum, maximum, and median percentages of the DNS requests that the top 4 most popular resolvers could observe during the 8 months of our experiment. In second place, we have exit relays that do their own resolution, which is what we mean by the word local that you see there. And they represent around 12% of queries coming out of Tor on average. In first place, we have Google's public 8.8.8.8 resolver that sees around 1/3 of DNS queries coming out of Tor on average. And at times, this number grew to over 40%, as you can see. We found this finding to be significant because it's alarming that one organization is getting to learn so much about Tor users' behavior. So the next question was, how can an attacker leverage DNS queries to identify which websites Tor users are visiting? We consider a threat model that's somewhere between end-to-end correlation attacks and website fingerprinting attacks. So remember, in a traffic correlation attack, the attacker can see ingress Tor traffic and egress Tor TCP traffic, and he attempts to link the two. In website fingerprinting, the attacker can only see ingress Tor traffic, which is encrypted, and he uses machine learning on it in order to identify the websites the traffic belongs to. So in our threat model, we assume that an attacker can see ingress Tor traffic and some egress DNS traffic, and not the TCP traffic coming out. So on the ingress side, the attacker can be the user's ISP, some AS on the path, or the guard relay itself. And on the egress side, the attacker can be an AS on the path or a malicious DNS server. And the idea here is now for the attacker to do a traditional website fingerprinting attack and then augment it with observed unencrypted DNS traffic in order to improve the results of the website fingerprinting. So to that end, we extended the WA k-nearest neighbors classifier from a Usenet security paper in order to come up with our two attacks. So in the interest of time, I'll only talk about our high precision attack. And in our high precision attack, we accept the WA-KNN website classification only if we observed that website in the DNS traffic that we collected. So this addition of DNS data makes our attacks more precise, and it turns out that our attacks work very well for unpopular websites. And that is websites that are lower on the Alexa scale. And this is problematic for dissident websites such as WikiLeaks, etc. So finally, we wanted to get a better idea of how our attack would work at internet scale, and for this we followed a well-established method. So we simulated clients from the 5 countries that have the most Tor users, and we placed them in the ASs of the country's most popular ISPs. Then we simulated their online behavior similar to Aaron Johnson's et al.'s CCS paper called Users Get Routed, and we made those simulated users visit several websites throughout the day. We used the Tor path simulator for Tor path selection, and then we ran trace routes for ingress Tor traffic and egress Tor DNS traffic using the RIPE Atlas measurement platform in order to get the ASs that we traversed. And then we labeled a Tor connection as compromised if it traverses the same AS on the ingress and egress side. So what's nice about RIPE Atlas is that they have many measurement probes in the same ASs as Tor relays, and we took advantage of this. So finally, we ran these simulations for 4 different exit relay DNS configurations in Tor. That is, what if all Tor exit relays were set up to use their ISP's resolvers? What if all Tor exit relays were set up to use Google's public resolver? What if all Tor exit relays were set up to do their own DNS resolution? And finally, what if all Tor exit relays were set up as they currently are, which we call the status quo? So here are the results of our simulations. This diagram compares the safety of our 4 DNS configurations for the exit relays. For each configuration, we have our 5 ISPs in the countries with the most Tor users. And distributions that are leaning to the right are bad. We want them to be as close to 0 as possible. So comparing our 4 DNS configurations, local DNS is the least safe one. And again, this is the one where the exit relays are set up to perform their own resolution. This makes sense intuitively as these queries spread around the internet the most, as we saw in that earlier example. All other configurations look somewhat similar, with ISP DNS being the safest, which makes sense because here we're assuming that the exit relay's ISP's resolver is in the same AS as the exit relay. Now, these results don't mean that we should send everything over Google or that all relays should use their ISP's resolver. Things are more complicated than that. So to that end, let's discuss a few countermeasures that we came up with. We actually recommend that exit relay operators avoid using Google's 8.8.8.8 public resolver so that Google doesn't get to learn so much about Tor users. And instead, they should either use the resolvers provided by their ISPs or do their own resolution, particularly if the operator's ISP already hosts many other exit relays. So for example, some ISPs like OVH host a disproportionate amount of exit relays already, and here again, we're having one entity that gets to learn a lot about what Tor users are doing. Furthermore, exit relays that are set up to do their own resolution can be further configured to minimize DNS information leakage by enabling query name minimization. So with QName minimization, DNS servers higher up in the hierarchy only receive the information they need to know to reply to the request and not the fully qualified domain name. So long-term solutions include adding confidentiality to DNS. For example, TDNS transports the DNS protocol over TLS and TCP. And deploying attacks against website fingerprinting attacks would be an important long-term goal too. Also, people can choose to use onion services. So now you know how DNS can be used to compromise Tor and what to do about it. So the contributions of our paper are that we discovered that DNS exposes Tor users' behavior to more adversaries than previously thought. We discovered that Google gets to learn a lot about Tor users' online activity. We created proof of concept de-anonymization attacks that demonstrate how DNS can make website fingerprinting attacks more precise. And finally, we performed simulations at internet scale in order to understand how our attacks could affect real people. So our work compels researchers to continue exploring how to make DNS more secure. And the moral of the story is that when you build a system like Tor, you have to look at the surrounding technologies it uses because they won't necessarily adhere to your system's security and privacy goals. So here's our project website where you can find our paper, data, code, and replication instructions. I definitely encourage you to check out our paper because we go into more details on this stuff and things I didn't have time to touch on here. Please feel free to contact me or any of my teammates, and I look forward to taking your questions now.
Roy Arends, I work for ICANN. Great presentation, thank you. Good research. I noticed Princeton being up there, right? Princeton University. Paul Smith, also Princeton University, just gave a brilliant presentation about oblivious DNS.
Right.
I think that it's kind of a good match for what you're trying to solve here. Is it an idea to include that in future research?
We should probably talk.
Yeah.
Yeah, no, yeah.
Cool, thank you.
No, thank you, thank you.
Hi, I'm Paul Wouters. I'm a Tor operator.
Oh, nice.
And I fall in the category C. My Tor exit node runs its own resolver, also with query minimization.
Okay.
It also enables prefetching, which means that if multiple users are fetching the same data, then the link between individual users becomes more vague because it will proactively keep that data fresh. So it's no longer linked to an individual Tor circuit user. So there's less of a mapping then if you do that. So maybe add that as one of your countermeasures in there.
Yeah.
And then in general, I think with Tor, it would be nice if we can get rid of the sort of the limited SOX proxy layer doing the DNS, because right now each Tor node client is vulnerable to DNS spoofing because they just get the unsigned DNS data over the Tor network from or depending on the exit node verifying the DNS sec. And you really want that verification to be on the client, the Tor node itself.
Got it.
And I've been talking to some people, and I'm supposed to catch up with them on it. So hopefully we'll hear about me.
Okay, perfect. Thank you.
Okay, so any more questions? If there aren't, I'm going to take advantage of this opportunity to slip in a question from here. If a website deployed an onion, a hidden service, there would be no problem, right? There's no DNS exposure, right? But for cases where there is no option for a Tor hidden service yet, if we just wanted to eliminate DNS as an additional traffic correlation vector, would it be a crazy idea to suggest that DNS authoritative server operators consider figuring out how to run an instance of their service inside Tor? Or is that too crazy an idea?
Whoa.
we can talk offline. I'm just
Interesting.
wondering.
Yeah, no, I mean,
Okay,
let's talk offline, but yeah.
Right. Okay,
yeah,
thanks.
Let's do that.
All right, thank you very much, Laura.
Perfect. All right. Thank you.
And our next speaker is Wes Hardiker from USC ISI.
All right, I'm Wes from USC ISI. I have 41 slides in 25 minutes, so I've really got to get going, but it's okay. I had coffee. We're going to make it. It's okay. So more seriously, I am going to go through sort of a couple of slides really, really quickly, because I want you to get sort of the high-level concept. We're really just going to hit the tip of an iceberg in a lot of these slides. I really want to get you the idea of thinking about this problem more than the actual details, because it would take an hour to go through them all in greater detail. So in 2017's NDSS, which was 2 weeks ago and a year ago, I sort of started thinking about, well, can we cache data longer than we should? And that really, and I showed that you can. I showed that you can actually cache like the Alexa Top 100 data for quite a bit longer than they'd really like you to, according to their TTLs. And that really got me to thinking, okay, but what do queries actually release? You know, and then, because I was coming up with a solution, and I realized I hadn't really defined the problem yet. So the question to me was, does query leakage going upward through the DNS tree actually, release anything that you don't want to have seen? So can traffic analysis release, find anything? Does temporal analysis find anything? And what solutions are available and how can they protect you? And so TLS and query minimization being the obvious ones. And then what techniques, protect you fully? So I'm speaking to the choir here with this diagram for the uninitiated, of course. Query minimization helps you by only, looking for .com and the answer, and then encryption enables you to, send encrypted queries. And really, there is no encryption between ISPs and the authoritative servers at this point. So that one's not even in play at this point in the first place. But what if you don't trust who you're sending them to in the first place? What if you you really don't trust the root? What if you don't trust .com? What if you don't trust the TLD? What can they see that you don't want them to see, even if you turn on query minimization? So I set up an experiment, and I took 2 residences, one of mine and one of my colleagues. We both run recursive resolvers in our houses because we are geeks like you guys. We both have static IP address. We were both willing, although when I asked my colleague, his definitive answer was, when I asked him, hey, can I look at all of your data? And then we were both able to provide ground truth, so we could sort of back up what I was trying to come up with real world data. So we did it between each of our houses, each of our static addresses, and broot, and I chose broot because we control both ends of the equation, so there was no privacy concerns at all in that case. And then I did some bulk global analysis. I didn't go deep diving into every single query. I wanted to see what could I do by looking for special things. So first off, here's some examples. Here's some statistics. Residence number 1 had a whole lot more packets than residence number 2. And you don't need to care about the numbers that much, but do note that IPv6 was 0 in residence number 2, showing that there is no v6 deployed there. So now this is where the fire hose begins of all of the data, and I'm not going to blast through the details so much, but I'm going to give you sort of high-level concepts. And so I analyzed RR types, I analyzed geographical information, I looked at timing constraints, I looked at special names within DNS just doing simple greps, and so that's what we're going to dive into next. So at residence 1, I analyzed all of the RR types. So this is all the RR types that we're seeing. You can see there's a bar graph. Not surprisingly, A and quad A are the most popular, but then text and NS and SOAs were really high. Well, it actually turns out if you dive into the text records for that, because I was sort of curious, why are there so many text records, right? The vast majority of them were searching for hostname.bind, id.server, and version.bind, and those types of things. You can guess what might be plugged in there? A RIPE Atlas probe. Very good. Yes. So if you look at the query frequency, you'll find that it's also very, very persistent in a flat. So it's clearly RIPE Atlas. So that's ground truth number one, right? RIPE Atlas. So if you remove the RIPE Atlas data, then you end up with a graph that looks a little bit more like what you would expect. It's all A and quad A like a normal thing. But then there's still all these little tiny things. If we zoom in to those lower ones, oops, first off, you know, there's some obvious things. If you look at the remaining text records, most of them are for domain key. And there's also MX queries. That kind of shows you what might be running in residence number one, specifically a mail server. And sure enough, there is a mail server in that residence. Diving down into the smaller ones, we ignore the tall bars on the left, and we see some more interesting types and very low query numbers, but this is, again, over a month's worth of data for stuff leaked to BRoot. So a couple of things. First off, you'll note that there is IXFRs, AXFRs, and DS records, which show that there's some validation going on. It shows that there is something is slaving the root. Not surprising, you'll see local root coming up a little bit later in the presentation as well. Residence number two, interesting data. It has quad A queries. Why is there quad A queries? There's no quad A deployed in the house. We determined that a bit ago, and I've also said that with ground truth. But there's still a lot of stuff doing quad A queries, even though they're unusable records. In fact, they're higher than the A queries. So also in residence number two, you'll find that there's pointer records, serve records, SSH, fingerprints, and name server records. Well, we already know they're running a name server because that was part of the experiment. But what about things like that serve record? Well, if you look at the one serve record, it turns out that it's querying for 10.0.0.38. Anybody that knows serve records know that's actually an illegal serve record, and that's not what they should look like at all. But anyway, it did release an internal address, so now I know that they're running a 10. address. So I'm attacking myself, or actually residence 2 is not me. I'm attacking my colleague, trying to determine as much information as I can about their network from a single source. I also learned that G2 was a name that came up for SSH fingerprints. And of course, when you do SSH internally to your house, you're going to do a query for, and it's going to go all the way up to the root, right? Now, I ask you in this case, would query minimization help here? Nope. I also did some geographical analysis. So I just looked at all the top-level domain, all the CCTLDs, and figured out where they were all going to. So this is actually a log-scale heat map, basically. And so Residence 1 spent a whole lot of time talking to China and Russia and Australia and Brazil, and I have no idea why. The reality is that it comes down to spam. This server has been a mail server for 20 years, and it gets a lot of spam. And the vast majority of it comes from these countries. Residence 2 is a little bit cleaner. It is talking mostly to Australia, and I asked my colleague about that, and he really has no idea. But it turns out that it's all coming from redns.net.au, which my guess is that is a DNS server for something else that he was querying ahead of time. So then I thought, well, let's look at temporal analysis, right? What happens if we bin everything over the course of a day? Can we find usage patterns? And if you look at Residence 1, you'll see that there's sort of this gap in the middle where queries go down. Okay, well, that could be a sleep period, right? That's when people aren't there, or possibly at work. That's the other possibility, right? It turns out that actually does map the sleep period quite well in the time offset. So these are GMT hours in the bottom, and that's about a 7-hour offset, which matches the location. The other residence sort of is not quite as clean. The gap is quite a bit longer. Maybe he sleeps more, I don't know. But it's still, you can still determine some data from it probably. I also looked at by day analysis, and so this is dividing up 28 days, so we got an even break across divisible by 7, and Sunday through Saturday. And as somebody pointed out at NDSS, I did not do a time shift, so technically these days don't perfectly elap with a time shift that I just came up with an analysis. But there's not really too much of a discernible pattern here. And so this is kind of a fail, but you could imagine that this would return results for a whole bunch of other people. My colleague is sort of the same way, not a whole lot of discernible pattern here. except that we both work at home. So it's not really surprising that when people are there all the time. But again, you can imagine that this type of analysis would work for other people. I also dived into some second-level domain analysis. What were like the top kind of things? And I just picked the top 20, and I said, what were they? What interesting things can you find in there? And in residence number 1, you note that use of fedoraproject.org was quite high. You note Samsung is high, RPM Fusion, VipCam is a camera manufacturer, which interestingly enough is an app that he doesn't have installed anywhere, so he's not really sure why that one even showed up in the DNS at all. But those are interesting things, right? So now I know there's a Samsung in his house, and by the way, I did confirm that. He does have Samsungs deployed in his house, and he does run Fedora. Looking at the public suffix list breakpoint, actually it breaks things differently, right? So the public suffix list, breaks down further down the chain based on where stuff occurs. Note that Fedora project actually dropped out because Fedora project actually is a public suffix list point. But you can see that Samsung is still in there. And in the other residence, Nintendo suddenly popped up because of it was lower than code.jp. Interestingly enough, there is no Nintendos deployed there, so that's an interesting side effect. I also did, I would love a one. If anybody wants to give me one so that I can generate more names, that'd be great, thanks. I also looked for names containing an underbar, because I figured, hey, those are unique, right? Very few names contain an underbar, let's look. So these are actually all of them during the entire month. There's not that many that leaked out. But note that I can tell a couple of things. One, there's some more internal address leakage. One of those is a Comcast address. Clearly somebody in the house, my son, plays Minecraft, because 3 of the records, 3 out of all of the leaked underbars are for Minecraft. And then there's a Jabber user, clearly, because there's an XMPP server query and things like that. So, lots of interesting stuff if you really want to dive in it. Again, I didn't go down to, all 50,000 queries, but I can imagine if I had really done the due diligence and looked through pages and pages and pages of name, I would have come off with more. These were sort of high-level aggregation type searches. So let's compare all of that analysis now to what mitigation options do we have for diving into this. How much do these things protect us? I've already shown that DNS query minimization doesn't protect you completely because some things will still leak. Although my colleague's G2 server, if you had NSEC validation, NSEC aggressive caching turned on, that would have actually solved that problem. TLS-based DNS encryption encrypts very well against the man in the middle, but not if you're sending it to the person that you don't trust in the first place. And then last time, a year ago, or 6 months ago, I presented on local root, which is a local copy of the root zone that you can run inside your resolver. And the address for that's down there at the bottom. If you want to consider signing up for it and getting a local root copy to your local resolvers, please go ahead and you can sign up your own resolvers there, and you'll get the benefits that you see on this screen, which shows for each of the attack types on the left and the 3 potential mitigation options across the top, how well do they do? Well, query minimization does fairly well for some stuff, but there's a whole bunch of stuff that because you're sending it essentially a TLD, right, that traffic analysis and timing analysis still works just fine. It really doesn't matter. I wasn't looking at the queries, I was looking at the frequency and things like that. TLS works really well, and they're all listed as partial because if you're sending it to the thing that you don't trust, that really doesn't help you very much. Still better than nothing against man in the middle. And then it doesn't protect at all against temporal anyway. And then finally, local root, which is basically having a copy of the root on your own system if you don't ask questions, nobody can analyze you. So this is actually what happens when you enable local root on your system, and those little tiny queries down at the bottom that still exist are actually from the RIPE Atlas that did not, use my local resolver for doing most of its querying. So you can see where it was turned on and then turned on and then turned back off again, how much the traffic loads varied between my house and the B root. So real quick conclusions, QNAME minimization and TLS only get you so far, and that doesn't mean that we should cache everything all the time. Where's the right balance? Where's the trade-off between what you might want to cache and what you might want to send? What sort of things do you trust? And this is really the tip of the iceberg. There is a ton more type of analysis. I mean, I did this rather quickly in a couple of weeks. If I dive down even further, I'm sure I could come up with more interesting stuff. If you want to give me your static addresses, I'd love to go play with your data too. That would be great. And more stories are needed, and I want to thank my colleague Robert for his willingness to, I promised that I would disclose anything embarrassing that I found, but I did not find anything embarrassing for his data either, fortunately. And distributing naming and push models, I think, are one of the things I think the future of the DNS or the future of naming systems kind of need to look into, and we're starting to explore that in a couple of spaces today, local root being one of them. It solves it only for the root currently. I have a student request out for a student that's willing to take on putting more data besides the root into my local root project so we can get some other TLDs. There's a bunch of other available zones out there, and eventually there'll be a checkbox of, which zones do you want to have advanced cached. The cost is bandwidth and memory. You're actually going to use up more bandwidth than you would otherwise, and then memory, of course, to run you don't want to run .com in your house. That would not work. But any questions? Lots of time. I could have slowed down.
Matt Poundset, speaking for no one in particular. If you would like me to speak for you, say the word. Just to provide some insight into your colleague spending so much time talking to Australia, ARI Services is a very large back-end registry operator and/or back-end DNS service provider to a lot of GTLDs, particularly in the new GTLD space. Right. Hundreds of them. So yeah, he's probably his son using a lot of .ninja domains or something.
Yeah, and if you look at a lot of these names, there's a whole bunch that are registries or things like that were clearly serving data for other zones. So that's not really surprising, and it would have been almost equally as interesting to look at the ones that only had single queries rather than the ones that had the most. But yeah, right.
Hi, Roy Adams, ICANN. I've always wanted to do something like this, but on my own data, I don't trust anyone else with my data, if that makes any sense. So it's very good. But just a funny side note, can you go back to slide 17? And in slide 17, you see that Resolver 1 is doing DNSSEC validation because there are DS queries. Can you go now to slide 37? The slide with the underscores. And you said all the underscores are there. There's no underscore TA dash. So you are basically running a validator that doesn't do 5011, right?
Yes, it is manually configured, I admit. Being the geek and deployed long before 5011 was written, yes, that's true.
No. Cool work, thank you. Sorry for the...
No. That was justly earned, thank you.
Ray Bellis, ISC. So your Nintendo queries? I suspect you may have a Pokemon Go player in the house somewhere.
I missed most of that. Could you repeat it?
Your Nintendo queries.
Oh, then
you may have a Pokemon Go player in the house.
That's a good question. So there was one. I don't know if it was being played in January, but that's a really good point. Thank you. Excellent.
Petr Špaček, CZNIC. If you want to play with something which implements local root and aggressive caching, go for the not resolver. We are just going to merge stuff which periodically fetches the root zone and fills local cache with it, which together with aggressive caching basically does everything for free without hassle of configuring local.
I need to put a reference to the ICANN project that's trying to push that into basically all the code bases to do that. The one advantage that local root gives you is that I will also, A, I'm going to do other stuff besides just the root, but B, it gives you notifications. So you will actually get DNS notifications to get faster update. Now for the root, does that matter? No, it really doesn't, but for other things it may.
Sure.
Okay, so I'll add one last trivia then for you. 10.0.0.38 is a DSL modem. It's the internal IP address that all DSL uses.
Huh, okay, did not know that. It's not my default, but okay. Thanks very much.
Okay, thank you. Yes? So I think we're all staying in this room. We need to do a little bit of work to prepare for the lightning talks. So bear with us for a bit.
who's first? Fred. Oop.
Good afternoon. My name is Frederico Neves. I work for nick.br. It's a pretty short presentation, a single slide. So, talking a little bit about algorithm rollovers. Okay, I only have 5 minutes now, but I've... 5 minutes till 5 minutes. Oh, okay, okay. So, as far as we know from the signer side, we only know 2 signers that implement algorithm rollover. It's bind managed keys and the OpenDNSSEC, and both implement the liberal method that is described in 6781. But 6781 recommends advice for the conservative approach. So we have this public log in October 2016 talking about the problems that we had in the past with the algorithm rollover. And apparently digging a little bit further, this was fixed 7 years ago. But 608040 is a document that I got to know yesterday that clarifies the language in 4035. So it's a 5 years ago document yet, already. But we have that logic telling us that it's impossible to prove that nobody implemented the conservative approach. So all this boils down to what is the safest way to algorithm roll a zone. So I think I did it in less than 5 minutes. So. I'm not looking for advice. I will not blame anyone that gives some answer and somebody gets screwed by this answer. But I will not hunt you, Peter, in the future.
Okay, so Peter Kortinik. Two remarks maybe. The one is when you say which is the safest approach, then you need to define safe for whom.
Oh, okay. And going unsigned is not an option.
That didn't.
Oh, safest for the zone publisher.
Say again?
Safest for the zone publisher.
Yeah, okay.
In their responsibility to keep the zone available for their customers.
Yeah, okay.
Or their customers' customers. Anyway, you got it.
Yeah. Which is, yeah, but that is trading safety for security on the side of the receiver. What I was going to is so this robustness principle has some perversions, which appear when what happened in the original version, the protocol specification says, you must do this, and at the same time says to the other side of the communication, but you must not check this, which is, of course, kind of weird.
I think the original language doesn't
well, probably not with that intonation that I used, but it basically says that. So when you say trade safety for security here, that decision is already made, right? So.
No. I actually, digging this in the last few days, I was inclined to do the conservative path, but not any longer.
Okay, this is Ulrich from IIS, the Swedish registry, and we just wrote our algorithm for the .se zone. And we didn't, well, it wasn't very conservative. We didn't introduce the signatures first. We introduced signatures and keys at the same time.
You guys did the liberal one.
Yeah.
Yeah, it's a double signing, basically.
Yeah. Yeah, we had the SIDN labs using the root canary, because it wasn't used for measuring the root rollover. They used it to measure the .se rollover. And I encourage you all to go to their website and read the blog post by Moritz about the rollover and what they measured. And it went very well. So they used RIPE Atlas and another tool to measure availability of the zone worldwide, and it went very well. So.
Thank you.
Hi, this is Robert from Packet Clearinghouse. I don't remember those documents so much in detail. Could you very briefly describe the difference between the conservative and the liberal? Because I would do what Sweden did and just double sign everything.
Basically, the conservative way of doing, because of this understanding of 4035 by this popular resolver, that was apparently, it doesn't look on the change logs that they were wrong, but they were like adopted a more liberal approach 7 years ago. Basically, what their more strict reading of the specification implies that the signatures with the new algorithm needs to be distributed in caches synchronously at the time of the publication. So basically what it advises, the conservative approach, is to first publish signatures with the new algorithm. Then after the TTL of the zone, those signatures are spread, you include the key on the key set. And then you flip the DS on the parent. And afterwards, you withdraw the old key algorithm from the key set, and then in the end, you withdraw the signatures. That's the conservative approach.
When you say add the key to the key set, is that as a DS record?
No.
No.
You put the signatures on the zone basically by the ZSK. We are talking about a split key here, and you don't put the new algorithm on the key set. You wait until the signatures are spread out. Basically, the old ones are expired from caches.
The old keys expire from the... Oh, okay.
The old signatures, yes, the old signatures with only the old algorithm.
Right, okay. Yeah.
It's only 2 extra steps. That's one of the reasonings that I thought it's no big deal to do all this.
This is always from my SEM. To explain the thing is like when you have, what the resolver did was if you have an algorithm in your key set, you have to have signatures with the algorithm. Yes.
Yeah, this is mandated by the signer.
Yeah, exactly. But so when you have the cache effect, you maybe fetch the new DS key, the key set. Yes, but then you don't have the new signatures in your cache. Right. Then it would say the record is bogus. Yeah. So that is why you would introduce the signatures first.
Yeah.
So did Sweden?
No, we didn't do that.
And you had no problems?
We had no problems.
Well, you don't know.
We did measure, so.
But you're not the user.
Anyway, thank you very much.
So our next speaker is Paul Hoffman, talking about DITL anonymization.
Not just DITL, by the way, any IP addresses, although it certainly is for DITL. So I mentioned this a little bit yesterday. I'm going to talk really fast because I know I have just 5 minutes for talking. Okay, I'm still going to talk really fast. So what I want to emphasize is the last bullet here, is that this is really a lightning talk. This is not explaining everything to you. If you think you understand it after this lightning talk, please don't believe yourself if this is new to you. RSAC will be publishing a document on this in the next few months. We hope. I mean, that is, RSAC caucus still hasn't moved it to RSAC. But what I'm talking about today is you have an IP address that you want to anonymize. We still believe in IPv4 and IPv6. Many people in the room have said, oh, I need to anonymize, and have come up with something, because they think it's easy. It is easy, but it's also, there are a lot of choices that if you said, oh, I know how to do this, you probably are ignoring things. What this quick presentation is going to go through 3 of the main proposals that are going to hopefully appear in the RSAC thing, and explain how to do them so that if you thought of one of them, hopefully you thought of one of the 3. If you thought of another one, certainly get to the mic line. But then you'll see what else other people are considering. So again, the document is not published yet and hasn't even gone to RSAC. These are the main 3. The first one is you cryptographically mix a new address with AES 128. You could also hash it. Turns out AES is a little bit faster. And then if for IPv4, you truncate. For IPv6, you don't, because AES 128 puts out 128 bits. So that's method 1. And I'll actually, the next 3 slides after this will go into each of these in detail. Method number 2 is you use something called CryptoPan, which actually mixes each address bit by bit and then truncates the bits. And the reason for this is you get some properties that you don't get with the main truncation. So the nice thing that you get out of that is that any of the output IP addresses where you have 2 addresses in the same subnet, that means they were in the same subnet coming in. So that helps researchers who are trying to see, a subnet that has more than one resolver in it or something like that. And then number 3, some of you have seen this on the DNS operations mailing list. Someone said, I forget, I think it might have even been Barrett, who said, oh, IP crypt. And so this is actually using IP crypt, which is, since it's only a 32-bit cipher, you use it for IPv4, and for IPv6 you use AES 128. Important note, you need a secret random number for any of these. And by secret, that means that anyone who knows the secret is going to be able to de-anonymize. So one thing people have said is, oh, maybe all the root server operators will pick the same secret number so that we can see things across, across, like, for example, a whole DITL set. The possible problem with that I've heard from some root server operators is, yes, but if that root server operator leaks the secret, my data is de-anonymized as well. So many people are saying, okay, we're going to have, each operator is going to anonymize and anonymize in their own way and such like that, which means that if you see in the output of one operator, or just even one data set, they might change the random number every day, a certain address, and you see it the next day, that does not mean that they were the same inputs. Okay, so let me go through these really quickly. The first one was mix and truncate for IPv4, or just mix for IPv6. This is pseudocode, but basically you do your mix. If it's an IPv4 address, you AES it, and then you just take the first 4 bytes of the output. But if it's IPv6, just AES it. So that's method 1. Note that when you do that truncation, you're going to get collisions, because you started with 128 bits and now you're down to 32. You will get some collisions, and we talk about that in the document. The number of collisions is fairly small. If your data set is small, the number of collisions gets much larger asymptotically as you get bigger. But for, say, 5 million addresses, it's well under 0.1%. Method number 2 is CryptoPan, where, as I said, they actually, and it's sort of hard to explain in pseudocode, but you actually take each bit of the input address and you do an AES on that, which means for an IPv6 address, you're actually doing 128 AESs. So that's fairly expensive, but remember, you only need to do it once if you're keeping a table of what I've already seen. Give and take. Now, and again, you get the advantages of that. It's called prefix preserving, but it takes a lot. And quite frankly, prefix preserving could also be privacy busting in the sense that if you're, two things that you can now see have a relation in the original address space, maybe you wouldn't have seen that, and you would not have seen that with number one. The third one is IP crypt, which is just, if you've got an IPv4 address, you run it through this function. IP crypt is an encryption function that was developed by a well-known cryptographer, and so people were like, oh, hey, this is really cool, this will do what we want. No one had asked for a public analysis of this, and so after there was discussion on DNS operations, I did, and just like it started raining analysis, including from the person who developed it. Was like, no, wait, I was doing that as a toy, So probably we don't want to do IP crypt, even though it's the simplest to explain, simply because you can actually leak the key. So again, there are advantages and disadvantages of each one. I'm not going to go into that. You might argue them at the mic really quickly. But there are advantages and disadvantages to different people, right? If you are the person who needs to anonymize, you're going to have a different threat model than the person who is a researcher who wants to have the best data where they can do interesting things. That's it. And he says that's it. So, mic line.
So I'm assuming that there is a hidden assumption here that an anonymous IP address should still have the same format of an IP address.
Exactly right.
Because otherwise you could do much easier things.
You could just do AES 128 on the IPv4 address.
You just start from number one of the first record, the first IP you see, and you call that number one, and you continue like that.
Yes, okay, so no, because, yes, you could do that, except if you are under a DDoS attack with randomized addressing, your lookup table then is going to be incredibly large.
Okay, so that's another hidden assumption you didn't mention.
Yes, is that you would actually want to have a lookup table so that you don't have to do this operation each time.
Okay, I look forward to all your hidden assumptions.
Okay, well, and they will be. Are you on RSAC caucus? Okay, well then, then you haven't been paying attention to my many requests for review. There's a current review request out, and you can see all the not so hidden assumptions. Sorry, Peter.
Peter Gordienik. I think that is a very good approach and would help lots of researchers and also people producing the data.
Which approach?
The general approach of defining this and giving certain options. I'm not so much into the details of the crypto functions, which I'm not sure that they matter so much, given the following two questions. One is, how would you envision these keys being kept or not, or applied over or what time?
You could throw them out. I mean, if you're the producer of this and you've anonymized your data, if you don't care about your data, just throw them away. Just forget them.
Well, that's the point. Anonymity is a nice word. Pseudonymity might be more appropriate. So don't, unless there is a long, interesting discussion in the paper about one versus the other, it might be easier to sell this as pseudonymity and not as anonymity, because that very much depends on how the keys are handled and so on and so forth.
Absolutely, and how they're shared.
What other properties the data have that might leak information, as we have seen in previous presentations.
Sure, absolutely.
So that's an important distinction to make.
Absolutely.
Wes Herdeker, USC. Just a note, especially to Paul, so half the purpose of keeping it a v4 address is so that we can put it back in PCAP. So like if you look at B-Roots data, we do anonymize using CryptoPan today, so all of the data that we've ever given to OARC.
No, I disagree.
Most of the data we've given to OARC, I don't know how far back that goes. We do anonymize. And
2017 wasn't anonymized.
Yeah, it was. I did it. But we anonymize only to the /24, and that might be what you're confusing.
Thank you.
So, yeah, because
whereas if you look at the iRoot one, which was really anonymized, that just blew all the record numbers away. So yours didn't. So yeah.
And so that's of course the research trade-off, right? Where do we draw that line of how do we balance research versus security, and there's no good answer there. The one that bothers me the most is the one where we end up with duplications and conflicts, because the uniqueness to me is half the interesting data that I would go query. But anyway, the point is that our PCAP files still work. You can still read them with TCP dump because we're putting them all back in 4 bytes.
Right. So again, this will be something, this is advice to RSAC members. They might pick different ones. One might pick number 1 and one might pick number 3. If they're doing a good job and they're not sharing their key, you can't tell the difference anyways. So the output of this, and a lot of this is coming straight from politics. You know, the GDPR versus this versus that. When do we do this? So if you want to anonymize, you can pick your own way. And again, the longer description is in the document. But be aware that it's very likely now we will have in any anonymized data sets, we will have no cross data set analysis. Because if you anonymize at all well using any of these 3, you just won't be able, you will not be able to compare from one data set to another. And again, some people are saying we should change the key every day. So if you have a 1 week's worth, you're not going to be able to even compare day to day. That's it? Great, thank you.
Thanks, Paul. Our next speaker is Peter de Vries, talking about bind testing with Meltdown Spectre.
Hello, Peter de Vries from Quotient. We've recently convinced our employer to migrate from Solaris Sun systems to Linux and Intel systems, and then immediately we're hit with Meltdown Spectre and threats of 30% decrease in performance, and got real worried that we weren't going to be able to meet our promises that we had made. So we did some testing to see how things panned out. Just a quick list of our parameters. We're running Red Hat Enterprise Linux 7. We have DL360 servers with dual Xeon processors. Our test environment, or our test scripts, we're primarily using DNS perf. We have a mix of queue types. We're running multiple DNS perfs trying to really simulate a high load on the system. So we are overtaxing it. We're getting a lot of dropped queries in the process, but that's intentional. This particular test set that I'll show is 70 runs of identical tests. They're 10-minute tests, a 1-minute pause, and we fully flush the cache in between. The 70 number is just arbitrary. It's a 13-hour run, which basically covered overnight while we were away from our desks. The bind RPMs are all custom built. We basically have the same parameters for all of them, so they should be identical. And the graphing data is based on DNS perf rather than based on bind stats, for whatever that's worth. So these are the results, and I apologize I don't have them broken down into individual graphs. The red line here is our baseline unpatched server running 999S10 at the time we did the testing, and the green line is right after we patched the server. That's all 3 variants: a hardware patch, a firmware patch for the processor, and the kernel patches for Red Hat. And surprisingly, we noticed a hefty decrease of 30–40% in the overall queries we could maintain. We then tried with 911.2p1, and you can see performance increased quite a bit. And then we reran the same test with 912RC2, and you can see performance was way up with that. So we're encouraged on what the future of bind holds. We didn't run any tests with 911.2p1 or 912 without the patch set installed, so I don't have any data on that at the moment. We did then go back and run 999S10 with the variants disabled, at least variant 2 and variant 3 of the patches disabled, and you can see at the bottom how we did the disabling of those. And if you can see through these terrible lines here, you can see that with variant 2 disabled, we almost get full performance back, and with variant 3 disabled, we get pretty much all of it. We did end up going with variant 2 is very customized towards virtualized environments. Since we're not running that, we're able to disable that altogether. And that's the data. So, questions?
Thank you very much. Tamar Gavrychenko from Creator Labs. Just for a clarification, the slide 2 reads that you were using dual Xeon E5 26 blah blah v4, which is Broadwell, and Red Hat Enterprise Linux doesn't have IBRS IBP enabled for Broadwell by default. This is my question. So on the last slide, you told that you are disabled IBRS. But was it enabled in the first place? Because on Red Hat, IBRS and IBPP are enabled by default only since Skylake, and you had Broadwell.
I believe our kernel flags were showing that it was enabled, but I would have to go back and double check that.
Okay, thank you very much.
Yeah.
This is Andre, I see. Do you know if you actually measure bind? Because the graphs show that you just tested bind, but you don't know what would, if that's an effect of the networking stack,
yeah,
or effect of running bind. So I think you should add some simple echo server and measure the effect on the echo server. So so you actually know where the variation, where the difference comes from, because it might come from like the bind running on the cores, but it could also be the kernel that has been slowed down for the UDP performance, or some interaction in between. Sure. So just measuring just one DNS daemon doesn't actually show what you are measuring. So there might be too many intervening variables.
Sure, agreed. And we only tested bind because that's all we're using at the moment, and it certainly could be.
This is what you care about.
Yeah,
but for the data, it actually doesn't say what.
Yeah, I understood. It may not be a bind problem. It's, yeah, like you said, it's all we care about at the moment.
Ray Ellis, also ISC. Can you go back one slide, please? Do you have any idea what suddenly caused the 912 to jump down?
I don't, and that's one of the things on our list to resolve. This was in the middle of the night. All these runs were run overnight while we were away from our desks. They are 100% identical. Yeah, there are a few anomalies I can't account for. That's the biggest one. There's also this weird little moment at 60 tests that, like, all of the tests had a decrease. I don't know why that would happen in this specific test scenario, but that's the data I have at the moment.
And were these 4 tests all run in parallel or consecutively?
No, these were run consecutively. Actually, the way they were run, it was 4 days, and they were run overnight. So it is a test lab environment. It's 100% isolated. We don't have latency changes. We didn't notice anything that really would have affected that. That is one of our big questions. Why did 912 all of a sudden flatline or change its performance? I don't have a good answer. I wish I did.
Yeah, I mean, one of the things I've been trying to find out, but with no luck, is over what sort of timescale the branch prediction algorithms within a CPU like that can actually take effect. I've heard potentially apocryphal stories of systems suddenly speeding up days after a daemon has been started, but that seems a little odd.
Yeah.
Yeah. I mean, I've done some benchmarking on this myself, not for Spectre, but just for Meltdown. There's a blog article on our website about that, where I was doing sort of quite high-load testing on authoritative stuff. So we didn't have any cache fill effects. It was pure authoritative data. And on that, we found essentially negligible difference. It's our typical in our performance lab, 600,000 to 700,000 queries per second, either way around. In fact, counterintuitively, in some of the tests, it actually seemed to get faster with KPTI enabled than without it. Just in terms of graphing the latency that was being seen,
yeah,
as opposed to the overall throughput. I think where I was going with that. Yeah, it's definitely a very puzzling result you're showing there.
Yeah. Yeah, agreed. And I have not rerun that 912. It was an RC candidate. We're not ready for 912, so we kind of went to focus on 999, which we were using at the time. I should note, I think you mentioned it, but all of our stuff was recursive. We maintain our authoritative environment. We didn't see a change in latency there, but the testing and the results are all from a recursive server. So.
Yeah, I think in the main reason, well, we talked about this yesterday, but for the benefit of the audience, I think the main reason that I believe we didn't see much results, sorry, difference in the results in my own testing, is because a high-end Xeon server, let's say before Meltdown, capable of doing 5 million context switches per second. With Meltdown, say maybe 2.5 million queries per second, sorry, context switches per second. And simply put, bind just doesn't necessarily stretch that. So the fact your system calls have suddenly become a certain amount slower doesn't really seem to have that much of an overall effect, because a lot of the stuff is actually compute bound. It's looking up stuff in red black trees and stuff like that bind is doing most of its work on, and not actually in processing system calls.
Yeah.
Thank you.
Thank you.
Thanks, Peter. Our next speaker is Wes Hardaker from USC ISI, talking about processing DITL data quickly.
All right, so I have 10 slides in 5 minutes, but the coffee's worn off. So analyzing DITL data, this is, after watching Paul's talk and talking about, converting to text format and then taking a whole bunch of PCAP data, I thought I'd explain how I usually start, because at USC ISI, we have a number of tools that kind of help me get started in research. So before I do something like go write a DNS cap plugin or something like that to do harder analysis over a whole bunch of TCP dump data, we have a whole bunch of stuff that sort of allows us to get started more quickly. And so I'm just going to give you a brief overview of what that is. And so the goal is just to show you another form of processing. It's not necessarily better or worse, it's just different. So, the more examples you have to pick from, the better. So we store all of BRoot's data locally too. Besides giving it to OARC, we store it locally. And so the examples today are going to be 2017, April 12th. And so we store it both as PCAP data, 250 gigs worth of data, and then we also convert it to a text record format, which I'm going to talk more about, and it boils down to about 96 gigs. And it's all accessible via a Hadoop cluster, and you'll have to excuse the line that, so I edited this in both OpenOffice and PowerPoint. That never goes well. So what that line said was it's a small cluster. We have 34 nodes in our Hadoop cluster. And it's mappable to SQL with Hive, and I'll give you some examples of that in a minute. And really some of the advantages of text records is when I actually did a comparison between, using DNS cap to look for data and looking through text, just generically on a single processor, it was about 3 times faster to look through text. And it's, it's human readable. You get to tools like Python, Awk, Perl, and you can search through Emacs if you want, And so that gives you a whole lot of power to implement stuff quickly and then, get around to it. Get around to doing better stuff later. So FSDB is our format, and I'm going to talk about that. The cons of the text format is that we lose ICMP data. We're only looking at DNS data. We lose bad packets. We're just tossing those out. And then we're storing query data, but we're not restoring all the responses. But for root data, who really cares? Because you already know what the response is going to be. So this is a link to FSDB, which is John Heidemann's long-term project. It's written in Perl because it started before Python existed, I think. And it's basically a tab-separated format, tab-separated column with a whole bunch of tools to go along with it. And so the top of every file has this header line that sort of describes the columns. For DNS, this is all of the records that we store in this file. So again, for all of our DITL data, we have all of this in an FSDB format. Don't try and read all that. That's crazy. But you can look it up, or I can give you access to it later if you want. So this is an example of the types of queries that I can generate really quickly. I did this over lunch. So I'm catting the encrypted file to db-row, which is selecting all the COMNet and orgs using a regular expression, and then casting it to db-call, which is just selecting just EDNS UDP size as a single column output from there, and then I'm sorting based on that, and then I'm running unique on it and counting that, and then I'm sorting based on the resulting count. So all of that, I could type very quickly, and I get this sort of output really, really fast. So this is looking at a single file from that DITL collection, and you can see that 4096 is the most popular EDNS zero size. You can also do some simplified Python. This is basically Python, which is just looking for the TLD string at the end of every name. And then it spits out name and account, and then this is something that takes all the names and counts and actually aggregates them all together again. The result is, so this is basically mirroring what Paul did in one of his slides, where he had a list of all the popular most TLDs. Okay, I wrote this over lunch. It ran in about 15 minutes once I fixed the bugs. You know how that goes. But now I can run it again and again on other DIDL collections too, and it shows that ComNet, root, local, org, ARPA, home, are all sort of the top queries. So as I mentioned before, we can also map it to Hive, which is basically an SQL interface on top of Hadoop, which is on top of ASCII text underneath the hood. And so this is select count, from 2017-04-12 with a name like %.com, and it's basically showing that there's 993 million records. And that whole query ran in 120 seconds. And so, some people have much nicer Hadoop clusters than I do that would run even faster. But, here's another example where I am looking for all the DNS OARC.net names that were sent to broot within that day, grouped by type, so that you can see that there were 40 queries for DS records, 3,500 for Quad A, yada, yada, yada. 2 for A6, by the way. Those things just never die. And so that ran in 151 seconds, so it's really quite quick. And it's nice when you have simple queries, you just want to go kind of test to see if something's going to work, whether it's worth diving into in greater detail. And the total CPU time is actually significantly more. It was 13,000 seconds, but that's because it's running on a Hadoop cluster with so many CPUs. And the speed up was about 88 times versus a single machine on a single CPU. So, why am I giving this in the first place? Again, like Paul was saying, being able to reduce all of that data down to a text file that he could process much faster is kind of critical if you want to do. Your chances of doing it just once and not having to do it again because you didn't make a mistake or you discovered something else you want to analyze is so high that it's always better to just spend the time up front to reduce stuff down to something that you can work with much, much faster. And a lot of times, it invariably means at some point you have to go back and write something that's bigger and better and can handle all the OARC code. All the OARC data. And anyway, one of the takeaways is that I think Paul said earlier, if you have simple queries, you just kind of want to know, is this worth exploring in greater detail? You can probably send them to me, and I'd be happy to do a quick test if it's simple. And Paul said earlier that you could send it to Paul or Warren, so that he could look at LRoot data and see if if it's worth exploring. Oh, it's Paul or Roy, not Warren. Yeah, you bet. Anyway, any questions? Roy's going to go all the way around.
Roy Adams, ICANN. We do something similar, except for the Hadoop cluster. So Paul has written his own tool, I've written my own tool, to basically take a PCAP, turn it into a text file. I get similar timings, but I don't use Hadoop. I use a combination of parallels.
I do that too for many things, yeah.
I didn't know about FSDB. I'll have a look.
Yeah, it's funny, and so as I said, John Heidemann wrote it, and I really didn't want to like it. I actually started off, I'm like, oh, it's Perl. I could do better than this. It turns out that they're really nice tools, and I use them like day to day now, even for personal data. I mean, I'm now addicted to them, so they're really nice.
Okay, I'll have a look.
Yeah,
sounds good. Thanks.
Okay, thank you.
All right, thanks, Wes. And our next speaker is Mr. Ruben Skul from Nick BR, and he's going to talk about GTLD name collisions.
Good afternoon, everyone. Just to alert you all that this is a schizophrenic presentation because it doesn't represent neither my opinion, my employer opinion, ICANN's opinion, or ICANN community opinion. It's just a portrait of what the GTLD policy community in ICANN is going through. Name collisions happen because starting 2000, ICANN started adding more TLDs than the initial legacy ones, and that has been causing collisions all around. In 2012, ICANN introduced more TLD, so this effect was more pronounced, but it happened all the time. It will happen again, possibly 2020, 2021, because ICANN needs to accept new TLD delegations, otherwise they will run into competition law issues. So it doesn't matter whether someone thinks that there is demand or not for more TLDs, they will come. And this talk is about a bit of what happened in 2012, a bit of what will happen. Just picking some piecemeals of this. In 2012, the name collision framework established of an idea of controlled interruption, get a wildcard record for 3 months in each zone that would break other people's systems that are getting name collisions. They will notice, they will fix those issues, they will move along. I can record the 37 occurrences of that, and none of them caused anyone to die. So we haven't stopped any device that was taking care of human life that was connected to the internet, which would be a bad idea anyways. Of those, most occurrences, they occurred in half of that, approximately, number of TLDs. They occurred even in some brand exclusive use TLDs that are not open TLD spaces. And they occurred in one geographic TLD like city names or city states, which was kind of lower than expected because the idea was that people with global networks used city names as part of their DNS hierarchy, but that didn't actually came about. There were no collisions in IDN TLDs, which is expected, which is unfortunate for IDN operators, which means that not that much people use IDNs anyway. We had about 22 days median between delegation and when it was reported to ICANN, but some of those took very long to report, like almost 2 years, but mostly they were fast enough to occur during the controlled interruption period. There were some disruptions, some effects on web applications that you can look at that. In most of cases, registry was not contacted. You can read all about later. What's the what I'm here for? To tell what's being thought of in the community, that instead of doing this as an afterwards exercise, that ICANN could do some drills or tests that would allow them to specify a list of names that, hey, these are names that you shouldn't apply to, or these are names that if you apply, you might want to take a look at it, like .home, .corp, .mail. All applicants would be able to say, hey, but this is how I will handle this, or I know about them, this is how I would handle this. And different from 2012, all low-risk strings would have a controlled interruption done by ICANN instead of the registry. So that could start much earlier in the process. And that could make the actual length of the interruption longer than 90 days if it's not delegated. We didn't have a consensus to change that from 90 days to either 60 days or 120 days, so defaulted to making that same period, but you might want to suggest something to that. And one of the issues that I would like to highlight is all decision-making would be data-driven within accessible data, like DNS OARC detail, original from JAS, but not from collections that wouldn't be available to researchers, like even icons on root servers unless I can make those available. So there were no actual consensus calls so far, only general agreements. So what ICANN community is looking most for DNS technical community? Suggestions on how to create the initial lists, or what to apply, what you shouldn't have for, how to assess risk in those strings that were applied for, how to assess if you file a mitigation framework, how to assess that, and also collision issues within legacy GTLDs that happen, as you might see in a previous presentation by Jeff Schmidt. So how to be aware, there's a link to the wiki page of this policy development effort that you can use either to see drill down of the data that I presented, or see how to join the work group, or you can just post to DNS OARC, DNS operations that will be relayed to the working group. I just need to ask you to not send this to my email, because this is a policy development effort, so there are transparency requirements within ICANN to do that. There's initial report that's coming this April, final report coming end of this year, and we also have a named collisions analysis project being run by ESSEC, so you might want to look into that as well. So that's about it. Suggestions for how to handle name collisions, besides not delegating new GTLDs, which would be the easier solution to the problem, but that's not on the table.
Any questions?
Comments? Hate speech?
All right. Thank you, Rubens.
Thank you.
And our final lightning talk for this afternoon is by André Souris from ISC about eDNS compliance deprecation workarounds. Together with Petr Spacek and...
They will dance around me. Hi, this is André at ISC. This is Ralph from Nelanet Labs. This is Peter from CZNIC. This is Peter van Dijk from Power DNS. He's just virtually with us. This is an effort that we talked about a year ago, that we need to unbreak some of the stuff on the internet by breaking more stuff on the internet. So here's the plan. The eDNS standard is really, really old. It comes from '99, and we, the DNS software vendors, have added various workarounds for broken servers. And the broken servers, from the eDNS perspective, is they either doesn't respond at all, or they respond with like non-compliant error code, and that would be form error. And the DNS servers, well, our DNS servers need to like cope with that, like keeping the list of what server is broken, which is not, and it's causing a lot of like code complexity, and the complexity is mostly wrong, and we want to keep things simple. So our plan is to basically, if you know eDNS, we would retry on error with eDNS again, unless we receive the form error, which would be according to standards, signaling that the server doesn't implement eDNS. It's been like 19 years, so everybody should be able to cope with this. This is coordinated effort by all of us, the CZNIC, ISC, Netherlands Labs, and Power DNS, and we would be happy if more like DNS vendors would join this effort. And basically, we would remove all the workarounds for the eDNS-related breakages from a certain date from the new software versions. And the date, the provisional date is 1st February 2019, so there's still plenty of time to fix your DNS servers if they are not compliant or if they are just broken. You don't have to implement eDNS, you just have to unbreak your servers. There's a test suite done by Mark Andrews. This is the website where you can test your zone and test your servers. There's a test suite that you can even compile yourself and test it yourself. And questions?
Okay, so let me add one more thing. We were talking about code complexity, right? And in Not Resolver, we didn't have many workarounds before. And just a week ago or maybe two, I found out that even the workarounds we had are broken, so they don't workarounding anything. So maybe it will not hurt that much. But anyway, test your servers.
You were always ahead.
My name is Andrew Sullivan. So that suggests that you could move this up. And I noticed that we're partway into March, which means that there's a prominent first of the month coming up. So since you've already gotten a start, you could just get going on this.
Hi, Dwayne Wessels from Verisign. Can you say a little bit about what's going to happen to people that don't fix when you make these changes? What's your prediction?
Well, probably they will be not able to resolve the domains. But okay. It usually means that their servers are broken anyway, so they are broken right now. Again, this is like shifting the costs.
Yeah.
And
I was just curious what the failure signal is going to be.
I think
it's
that
like nothing will
they won't be able to resolve those domains.
Certain names won't resolve, or all names won't resolve.
Yeah, I think so that's going to happen.
Yeah, maybe it's important to know that this plan is about the new releases after that date, right? So it will be breaking gradually as people will be deploying the new versions. Or maybe will not be deploying the new versions, right? It depends, but you either want new features and security fixes or keep old broken stuff running, so you have to pick.
Peter Kordinik. So this reminds me a bit of World IPv6 Day, just in the reverse, right? Yeah, that's going to coming. So you asked for more vendors to join. First of all, I think it's good that you join forces and fight this complexity. Good move. You need the buy-in of the operators and of those folk who are both, right?
Well, we don't, because most of the world is okay. It's just a couple of bad apples in a basket. So most of the world is just fine, and I think that the impact on the end user will be negligible unless you visit that special site that's actually that broken.
Yeah, but everybody is special in a way.
And also, I would like to emphasize what Peter said. This is not. We are not implementing a kill switch that would check the date inside the DNS server and stop resolving that on the date. It will be only the new software versions that will be released after the date. And for example, for Red Hat folks, it will mean this will happen in 10 years or something. But that's same for all the stable, say Debian has the same policy, so it will the people will gradually implement the new versions, and there will so Word will not break on the 1st February 2019. It will just be the next releases that will be implementing or not implementing the workarounds.
Yeah, that is true, but the bigger question is how backwards compatible do we want the infrastructure to be in an internet that has update cycles of days or hours elsewhere, right? And that's a discussion. What I'm trying to suggest here is that you level up the discussion to this bigger question. to address more people, or to reach out to more people making these decisions and understanding how they are affected from this. Weighing in, of course, the overall complexity, which again is tragedy of the commons, kind of not a pain felt by the end user and less so by the operators.
Let me reiterate that our workarounds are broken, so they don't work around anything, and apparently the sky didn't fall down, so it's not that big breakage.
Hi, this is Robert from PCH. I like that you're doing this, and I think it's less harmful than so many other things, because in this scenario, at least there's somebody by the computer doing the upgrade. So hopefully he will figure out that he broke something. Otherwise, maybe he's not worth it sitting there.
Yeah, but basically, I think it is important that we draw the line and we say this is as far as we go for the breakage.
Do the same for IPv4, please.
Well, yeah, this is like I've talked about this before, but I think that we need to like gradually reduce the complexity in our software, in the internet, and I think this is like the first step, and that's why it's coordinated between the vendors. That this is coordinated effort between us, and really we would like to like the OpenDNS, the Google Public DNS folks, the Quad9 to join us in this effort. So this is like and Microsoft perhaps.
Andre, is this Federico from Nick.br? Is this one of the reasonings for your argument against ATR?
No.
Okay.
But this is just my general mindset about. But it's not directly related. But I dislike complexity in DNS. I probably have chosen wrong protocol.
Any other final questions or comments? If not, I have one comment for you guys. I really like the idea that you're doing this, and I like that you're coordinating this as a group of vendors. I think one important thing in this effort is communication that shows the vendor unity. So, for example, when you release your new versions where you've removed all the workarounds, the release notes would be helpful if they said, we're not the only ones doing this, and it's not going to help you if you switch to Unbound or not or something like that, because you're getting the same thing there. So,
Good idea.
Because you are beyond help.
Yeah, as in make it clear that this isn't one vendor, and that this is a joint effort by lots of vendors, and you're not going to be able to hide from this.
Yeah. Thank you. Thank you.
Thanks, guys. That concludes our lightning talk session. And I'll hand over to Keith now for closing remarks.
Okay, it's Friday afternoon. It's nearly Friday evening, so you've all been extremely good in sitting through 2 days of workshop, so I will not detain you for long. First of all, we really like to get feedback on the content. That feeds into the program committee process so that we can get content that matches what you were interested in. Unfortunately, the chimps at SurveyMonkey mangled the survey yesterday. So I apologize for the delay in getting the surveys up. I know quite a lot of you are still around for ICANN, but if you could please take the time to complete the surveys. There's one on all the talks. Really all we just need is one to 10 number per talk for feedback in that, and another on the meeting logistics. So again, sorry that we didn't give you the chance to do that before now, but if you could please take the time to do that, that would be great. Really, the main thing that remains to me is to thank everybody. I mean, you all contribute to OARC in all kinds of ways, but I know it was a non-trivial challenge for some of you to travel here at this time of year. So thank you all for being here. In particular, I'd like to thank ICANN again for hosting the event and basically providing all these great facilities and assistance and catering for us. Also to thank Salesforce for contributing to the sponsor last night. To thank all our speakers. Our speakers all come here on their own dime and their own time. Without them, we would not have a workshop. So thank you to all the speakers. Thank you as well to the various volunteers that have helped out. Dave and Maurizio with the webcasting. We've had a lot more webcast viewers this time round. And also Matt for his help with the PGP signing and various other people that have pitched in at various points to help us out. We've had 97 attendees, 17 of them are first-timers, so thank you for the first-timers for being here. I hope we all made them welcome. Somewhere around 40 remote viewers, and also one amphibian. OARC 29, slightly longer than usual because this was early in the year, will be in Amsterdam. It will be jointly with the RIPE meeting, which is something we've done before and generally works very well. We're also doing something that we haven't done before and we've wanted to do for a while, which is to make it jointly with the Center Tech workshop that often happens before RIPE meetings as well. So look forward to seeing you all in Amsterdam. And really, I'm sorry? Yeah, we're definitely going to do it on the 13th and 14th. We'd ideally like to run to 2.5 days so that we can have a little bit of separate time for Center and OARC. But we can only afford to do that if we get sponsorship. So if you're interested in sponsoring the meeting in Amsterdam, then we'd appreciate that. Otherwise, it will be the Saturday and Sunday before RIPE as usual, and we'll squeeze it all in somehow, including the AGM. So if you could join me in thanking everybody that contributed to the workshop. At least some of the OARC staff will be around for ICANN, so if you're around, we're certainly available to talk. And again, see you all next time.